Hello, this is a question relating to the analysis of a slider crank mechanism. Consider a slider crank mechanism given below, where at this instant, the crank, which is linked to, rotates counterclockwise at a constant velocity of 200 rad per second, and the angular positions of the crank from the fixed link is given to be 40 degrees. The external force acting on the slider is given to be 20 pounds, and you're to assume that the weight of the crank and the coupler to be negligible. The first thing you're required to determine is the linear acceleration of the slider, and to find this you need to use the relative acceleration method. You're then required to determine the angular acceleration of the coupler, which is link 3. Then, assuming the weight of the slider to be 2 pounds, you are required to determine the inertial force acting on the slider. So for this kind of question, the first thing you need to do is you draw the space diagram of the mechanism. So for you to obtain the space diagram, since you know the angular position of the crank, you know the length of the crank, and also you know the length of the coupler, you easily draw the space diagram using a suitable scale. So for this case, I used a scale of 2 centimeters to represent 1 inch. So the angular from my space diagram, I obtained the angular position of the coupler from the fixed link to be 13.8 degrees. After drawing the space diagram, the next thing you need to draw is the velocity diagram. Before you draw the velocity diagram, you first need to draw a line perpendicular to AB, which represents the velocity of the crank. So you draw just a line perpendicular to AB, and similarly, you just draw another line perpendicular to BC. So, since you are given the angular velocity of the crank, so the velocity of the speed of the crank will be given by the omega b times AB. So it comes to 300 inches per second. So this is represented by AB. AB, this is the line perpendicular to AB from the space diagram. So using your set square, first thing you need to draw just a line A from point A, just a line of a known distance, and using a name point A. Using your set square, you transfer this perpendicular line to point A, and the distance given is VB, that's 300 inches per second. But using a suitable scale of 1 centimeter to represent 100 inches per second, you draw this vector VB. Then from point B, you draw a line perpendicular to BC. You transfer it using your set square from point B to intersect the line drawn earlier. So VB, this line BC represents the velocity VBC. From the measurement, it comes to 240 inches per second. This is just the velocity diagram obtained from this space diagram. Then the next step, you'll have to come up with the acceleration diagram. But first, before you draw it, you need to calculate the accelerations which can be obtained from these velocity diagrams. The first one is acceleration AB, which is obtained by this formula VB squared over AB. So if you input the values, you obtain 60,000 inches per second squared. Next one is ACB, which is obtained by VCB squared over BC. And you already obtained VCB from the velocity diagram. So it's 14,400 inches per second. Then drawing the acceleration diagram, you use a scale suitable to you. So for this case, I used a scale of 1 centimeter to represent 10,000 inches per second squared. So the first thing, you need to draw a line perpendicular to AC from the space diagram. Then from point A prime, you draw a line parallel to AB. So it's this line. Just transfer a line parallel to AB from point A, and the distance is AB. It's the acceleration AB calculated earlier. This is 60,000 inches per second squared. Then after that, from point B, you draw another line which is parallel to BC. Just transfer a line parallel to BC from point B prime. And you name the measurement of this line will be given by this acceleration calculated, that is 14,400 inches, 14,400 inches per second squared. So this is the distance. Then after that, you draw a line perpendicular to B prime X. If you draw this line, you draw a line that intersects the line parallel to AB, which was drawn earlier. So this line intersects it at point C prime. Then to obtain the linear acceleration, to answer the first question, the linear acceleration of the slider, we know that for you to determine the linear acceleration, it is the composition of the tangential and the normal component. So the linear acceleration of the slider A4, it's AC, which is the tangential component plus the normal component. So this equation is just the relative acceleration if you are to calculate it. But since you're using the graphical method, the linear acceleration of the slider is given by the line A prime, C prime, which from the diagram we obtain it to be 50,800 inches per second squared. That a first part of the question has been answered. So the angular acceleration of the coupler, link 3, it's obtained by the linear acceleration of the coupler divided by the length of the coupler. So first thing, you need to measure the linear acceleration of the coupler from the acceleration diagram, which comes up to the 6,300 inches per second squared. Then for the angular acceleration of the coupler, just divide it by the length of the coupler, which is 4 inches. For that, you'll obtain to be 9,075 rads per second. That's the angular velocity acceleration of the coupler. Then part C, where you're required to determine the inertial force of the coupler. This is just the free body diagram of the slider, and this is the required inertial force that you are supposed to calculate. So the inertial force is obtained by multiplying the mass of the slider by the linear acceleration of the slider. This equation gives us the inertial force of the slider. So using the gravitational acceleration g to be 386 inches per second, the inertial force will just be the mass of the coupler times the linear acceleration of the slider divided by the g given, which is 386 inches per second squared. If you do this, you'll find the linear acceleration of the slider to be 263.2, acting in the 0 degrees direction. Thank you for listening.